So now it's time to start our unit on bonding. And it's probably a good idea to take a look back at where we began the year, talking about matter, which is made up of both elements and compounds. A couple units later, we dove into the periodic table where we were talking just about the elements. And now we are up to bonding, and we're back to elements and compounds again. So it's sort of coming full circle. Probably a good idea to review one of the more common terms this unit, the compound. The compound, we said this before when we were in unit 1, compounds involve different elements that are chemically bonded together, as opposed to mixtures, which involve different elements or compounds that are physically combined. So in this case, we have atoms of different elements being chemically combined. And that takes us to the next term, which is the bond. And that chemical combination is based on a force of attraction. And this is where a lot of people get confused because they think that electrons, we use the term electrons pairing up. And so people think that electrons are attracting electrons, but that's not the case. It's actually an attraction between the protons of one atom and the electrons of another, right? So it's an interaction between positive and negative. Right? That attraction is what pulls atoms to one another. We said all along when we've even just mentioned bonding in the periodic table unit that it's only the valence electrons that participate, the outermost electrons, the electrons in the valence shell, and that when bonds are formed, and I'll add the word new, when new bonds are formed, that constitutes a chemical reaction. And the reason I put the word new out in front, when we were talking about mixtures, we said that when something's dissolved, bonds break temporarily. You boil off the water and those bonds reform, but those aren't new bonds. Those are the same bonds that were there before, so that didn't constitute dissolving and recombining doesn't constitute a chemical reaction. In this case, we're talking about the reorganization of elements and the formation of new compounds and molecules. Briefly want to talk about the law of conservation of energy and mass and charge, the first law of thermodynamics, and it sounds a lot more intimidating than it really is. Basically, what it means is that whenever we have a chemical reaction, three things: energy, mass, and charge all have to be conserved. None of them can be created or destroyed. That's where the term conservation comes in. What that means is that energy can be gained or lost. It can be a reactant or a product. It can enter the system or leave the system, but it can't be created by the system. It can't just appear out of nowhere and it can't disappear. The same is true for mass. Um, the different atoms and molecules can be rearranged, but the mass, the total mass of the reactants, has to equal the total mass of the products, and the same is true for charge. Any electrons lost by some atoms have to be gained by others. They can't just disappear. Now, the octet rule. We've mentioned this all along. 8 is great. 8 valence electrons is sort of the goal for atoms of all the elements, no matter what period or group. Elements seek to achieve we call it a stable octet, and if you take AP chemistry with me, you'll learn that a stable octet really, there's no such thing. I heard a guy refer to it as 8 singing horses. Thought it was kind of funny. Um, but it's a good concept. It just so happens that every time we get to 8 valence electrons, our pattern repeats. So 8 is great, is a really good theme. It helps us learn the concepts initially. And then, like I said, when you jump into AP with me, we'll dive into the mechanics involved there a little more. Now, the noble gases. The noble gases already have 8 valence electrons. And that's why they're inert. They don't tend to react or bond. It's not to say that they can't. That's why they're called the noble gases. They kind of leave all the other elements alone. However, even the noble gases will form bonds. So if we take a look at this question here, uh, try to figure out, looking at the snippet of the table that I put to the left, which of these noble gases you think would form bonds most easily with another really active element on the periodic table. And there's clues. First, we just got done with the periodic table unit. So you know as you move down a group, things, uh, well, elements tend to lose electrons more easily because of increased shielding. Also, another clue on here are these, which we haven't really talked about until now. And those are the oxidation numbers. Those are the possible charges that an element can have within a compound. And if you'll notice, helium, neon, and argon don't have one. That's because helium, neon, and argon just don't form bonds. They're, of all the noble gases, the least active. But as soon as you get down to krypton, you'll notice that it has a possible charge or an oxidation number of +2. That means that's the first of the noble gases that we would say has a tendency to react. Even though it's a noble gas, it will react. And the reason is because of the fact that it has a high level of shielding. Of all the elements in that list. Now, xenon, if you look at the 3 possible charges xenon has, that's even more active. That's because xenon has a higher level of shielding than krypton. And radon we won't get into because radon's radioactive. Which element do you think would be the most likely out of this list to react with krypton? Well, if krypton wants to become, +2, then you're looking for something that is most likely to take electrons from it, or would be the most electronegative, and that's the Grinch, our greediest element of all, fluorine. And why do you think that is? We just said it, because that's the element with the highest electronegativity. Longest word you'll have to write all year. Okay, next up, we're going to talk about energy and bonding. Okay, that's your bond, the link between two atoms. Atoms of different elements, could be atoms of the same element. If we're talking about a molecule. Spontaneous bond formation. The word spontaneous means it happens on its own. And I don't like the fact that the Regents refers to spontaneous bond formation as exothermic. They link these two terms together. Usually it's true. It's not always true. Again, you'll learn about more of that in AP when we talk about something called entropy. But for all intents and purposes right now, when bonds form spontaneously, I want you to understand that energy is generally released. And the bonds then go from a high energy, sorry, I underlined the wrong one first, from high energy to low energy, and that they become more stable. So the energy goes downhill like this, and the stability goes up. Right? Less energy means more stable. Think about climbing up a tree. The higher up you go, the less stable you are, and if you fall from really high up, you're falling with a lot of energy. The more you move down the tree, the less energy you would have if you fell. It wouldn't hurt as much when you hit the ground. And the lower you are on that tree, the more stable you are. Any chemical reaction that gives off energy, where energy is released as a product, is called an exothermic reaction. Okay? The products are on this side. And you can see energy is on the product side. Okay, to the right of that arrow, which is just like an equal sign in math for a chemical equation, to the right of the arrow are the products. And if you see energy on the product side, then you have an exothermic reaction. If you look at this reaction we have down here, we're going to do a little activity called It's in the Bag. And combining calcium chloride and baking soda in solution, we get a chemical reaction. And in the bag, when you're holding the bag in your hand, it'll feel hot. That's because the system's giving off heat. Heat is exiting the system. Exo means out of, thermic means heat. Think thermal, thermos. Now when we go to breaking bonds, and we say this is not spontaneous. In order to break a bond that's already formed, energy must be consumed. This means we're taking something from low energy to high energy, from happy to unhappy. This is ripping two atoms apart, and it requires energy. Again, think about ripping the atoms apart. They're connected, they want to be together, and we're breaking them apart. These we refer to as endothermic reactions. Endo or into, again, thermic meaning heat. And now you're looking for energy to be consumed. That means it's an ingredient. I kind of buried that word over here. It's an ingredient. The ingredients in a chemical reaction we refer to as the reactants. Okay? If you see energy on the left side of the arrow, it's a reactant. That means energy goes in. That means it requires energy for the reaction to occur. And that would be an endothermic reaction. When you break an ice pack, it feels very cold. The reason it feels cold is it's taking heat from your hand to make the chemical reaction inside the bag occur. So you feel cold because, again, the system inside the bag is removing heat from your hand. It's using heat from your hand to cause a chemical reaction. And so you have an endothermic reaction that cools your hand, and you have your hand that provides the heat for the process to occur.